I'm the Technical Director for Energy Center. Welcome to today's seminar. It's kind of nice having a smaller crowd. It's very much more intimate, I think. I'm sorry. Today's speaker is Therese Peffer. She is a research coordinator and a colleague of mine at CIEE. She also works with me in support of the I4 Energy Center. And many of you have probably seen her before. She substitutes for me when I'm on travel hosting this seminar. Her research involves projects here, both here at CITRIS and at the Lawrence Berkeley National Labs. Her focus is on energy consumption displays, thermostats, and consumer behavior. She earned her BA in, of all degrees, neurobiology and psychology here at Berkeley. Then she sidetracked to the University of Oregon and got her master's in architecture, and then returned to Berkeley to receive her PhD in architecture in 2009. So let's welcome Therese.
Thank you. Thank you very much. Thank you for coming. I'm going to combine two projects that have to do with thermostats in this talk. And so let me move further here. And I want to credit, oh gosh, so the top is not showing. Can that be fixed? Do you know? Okay, thanks. It says contributors. So I want to credit the research groups that I work with. One is Dr. Alan Meyer. I've been working with him for about 3 years up at Lawrence Berkeley National Lab. And he put together just a fantastic team to look at, we're calling it climate control. So this is kind of beyond thermostats, or another moniker for thermostats. And he put together an incredible team. Cecilia Aragon, who used to be a professor at the iSchool here and was also working at LBNL. Now she's up at University of Washington. Marco Bertoni, who actually, if this is webcast, he probably is watching from UC Davis. So he's a PhD student there at UC Davis. Daniel Perry, who was a master's student at the iSchool here and is now a PhD student up at UW. So the research that I'm going to be describing was funded by the Department of Energy and the Environmental Protection Agency, EPA. And the second project I'm going to be talking about was really stemmed from this it's a project, the State Projects Partnership for Energy Efficient Demonstrations. Carl Brown discussed this as an I4 Energy seminar a couple of months ago and really talked about what was happening with this project. Basically, the idea is to take CEC peer technologies that have been vetted through the peer program and to kind of roll them out into campuses to really increase the market share by pushing them first through campuses. And so Carl Brown and Carl Johnson of CIEE asked me to look at advanced thermostats and see how we could apply these to campuses. So I worked with Jonathan Woolley, who is working at the UC Davis, the Western Cooling Efficiency Center, and basically was responsible for analyzing a pretty recent installation of occupancy sensing thermostats at the dormitories there. So I'll be talking about those two things. I'm going to start with just a little bit of history. I'm not going to go back 400 years, but really start with the Honeywell round. Manual thermostat is what we call this. You have to actually go up to it and do something. But it's in terms of market share, I think they're still being sold. It's a very popular thermostat, pretty easy to understand and use, very, very simple, a couple of switches and then just the dial. You've probably seen rectangular forms of this manual thermostats too that are still around. And then, although you can see here, step-back thermostats have been around for 100 years, it was really this policy after the energy crisis in 1973, the state of California developed these energy codes in 1978. And part of the energy code was called Title 24. Part of the energy code required these setback or clock thermostats. And basically, these could be set to turn down your temperature set point at night so the heater wouldn't run as much, so you would be saving energy. And for those of you that are interested in, and it was based on some research that suggested you would get this 1% savings per degree Fahrenheit for an 8-hour setback. And this is significant in that, at least, I don't know what the data was back in 1978, but current data shows that residential thermostats control about 9% of US primary energy consumption with respect to heating and cooling homes. So if you can save 1% or more, that's a nice effect there. And in terms of, if you want to look at the effect of policy in California, well, If you look at the numbers of programmable thermostats or setback thermostats out there, across the US, it's something like 34% of people that own thermostats have a programmable or setback thermostat. And in California, it's more like 54%. So you can see the policy really had a big effect in moving this technology forward. And so by the time the 80s rolled in, you started seeing this kind of white plastic box with a small screen, going from a mechanical system to electronic. And the EPA jumped in 1985 here. As I'm sure you have seen the Energy Star label on different appliances, whether it's your LCD screen or a fan or a television or what have you, and they put the Energy Star label on thermostats. And this comes with a set of requirements. So it's not only just a quality control, but it says something about the energy savings of the device. And then this, thanks to Ron Hoffman, who alerted me to recent consumer reports on thermostats. This is their top of the line Venstar thermostat. It's full color, it's touchscreen. It also, I think, functions as a picture frame. And so this kind of shows you the state of the art and so where we've come just in 60 years. And this is, I think, where I think it's also communicating to. So it shows where technology is really going, because in the last decade, you've seen a lot of advanced controls, multi-zone, being able to control humidity, learning algorithms, not only about the house itself, the equipment, but user preferences and schedules, price, so demand response, being able to adjust to a price signal. The screens got larger, more touch screens. Communicating was a big part of this too, being able to control your thermostat with your smartphone. So a lot has changed, and I think one of the things we've been very interested is seeing how this affects energy. About 3 years ago, the EPA discontinued the Energy Star label for thermostats. And this was based on research that they did, looking at a number of different studies over the past decade to look at, do these thermostats actually save energy? And so I'll show you some of the findings. They found that programmable thermostats were pretty much being used like manual thermostats were, right? And so if you gave a programmable thermostat to someone who already set back their thermostat manually, well, they were going to program it and use it to do the same thing. But it didn't. It wasn't magic. It didn't change behavior, and the behavior really was what was driving the setbacks. They also noted a number of things that had to do with usability. So they noted a number of problems with programming. Not only it inhibited users, so they not only couldn't they couldn't program, but they didn't want to program. It wasn't engaging enough to them to even want to interact with it. There's a lot of terms like set point and programmable that people just didn't understand. It wasn't an intuitive use of the word. And overall, you can see there was just, people just weren't using it, and they felt that it was behavioral reasons. It wasn't, it had to do with the usability of the device itself. And so that's where Alan Meyer came in. He got a grant from the Department of Energy to do a bunch of research in this area. So we started off with a literature review, and we did basically a number of different investigations. We teamed up with a weatherization crew in the Midwest to, when they went in and actually installed a thermostat, we asked them to take a picture of the thermostat that was there already and to administer a short survey. Marco Bertoni did this wonderful work with Amazon Mechanical Turk. So this was a survey and photo upload. We actually paid people pennies to upload a picture of their thermostat, which was wonderful. We could start looking at, people say, oh yes, I programmed my thermostat, and we would look at the photo and it said it was in hold mode, which basically turns it into a manual thermostat. So this was very informative. And he's got a paper, I think it will be published in the next few months. I think it's in Energy, the journal. We did a traditional online survey, thanks to the Center for the Built Environment across campus. And then we conducted this usability test. Now, Alan Meyer talked about this about a year ago in this seminar. So I'm basically going to summarize for you what happened in one slide and then tell you about the work that went on beyond that. We had 5 interfaces, five thermostats, 7 tasks, 31 subjects. They were recruited from Craigslist. 2 interfaces each. We videotaped the test, and there was a test administrator that was actually sat there and took notes. A lot of analysis, a lot of time analyzing. And basically the results were, we developed this numeric, we developed a number of metrics, but the one that we provided to EPA and thought that would be the most useful to them was this time to complete and success metric. So it combined how long it took someone to complete a task with whether they were successful, whether they actually accomplished what the task set out to do. And we were able to use this to reflect the thermostat's usability. So a ranking of 0.9 meant it was really usable, and lower rankings meant the thermostat was not as usable. And Daniel wrote a nice paper about this. It was about a year ago in the Journal of Usability Studies. But my question was, well, what about these thermostats either helped the usability or hindered it? What helped people perform these tasks, or what prevented them from performing the tasks? So that's really what I'm going to focus on right now for the next few minutes. And now this is my caveat. Even though I'm going to be talking about usability, I want to show that usability isn't the whole story with respect to whether people are going to use these programmable thermostats. I think the case of cell phones kind of shows this as well. You could get a cell phone that's not very usable, but because of the utility of it, people want to use their cell phone. It's going to overcome any barriers to usability. So there's that factor. And if people see a high utility, that's going to overcome any problems with usability. Another issue is social acceptability, too. I think about the Nest thermostat and the people that purchase those. Consumer Reports didn't list them as high in terms of the rankings for usability. But I'm going to bet that if someone goes out and spends the $300 on a Nest thermostat, they're certainly going to use that as a bragging point. It's a beautiful thermostat. It's something that you're going to be proud of on your wall, and you're going to learn how to use it if you see any problems with it. So you have to think about other factors other than usability. And now I'm going to focus on usability. So one of the things I started with was looking at, well, what guidelines are out there specifically for programmable thermostats, but also zooming out a little bit and seeing what other guidelines I could actually use to help guide this analysis. And so I picked up an ergonomics textbook and just looked at it. It talks about font size and contrast and things like that, dexterity. Looked at just general device interface usability. Norman's work, maybe you've heard of him, Donald Norman. Computer-human interfaces. Thermostats are really like an embedded device these days. It's really a dedicated computer anymore. So that was useful to look at that. Commercial building controls is another area I looked at, as well as I did find one PhD student in Finland that had done his dissertation on commercial building thermostats and usability of these. So that was very, very useful. And you don't have to read through all these, but there were quite a bit of overlap. And so one of the things I did was first just kind of go through all these different guidelines and see where they overlap, like the visibility of available options. Both Norman and Paulson and Lewis talk about feedback from controls, match between system and real world, or consistency in standards, error prevention, recovery, aesthetics. Just in terms of, and many of them mention this, minimalist design, and then help and documentation. And so now I'm going to go through the different thermostats. There were 5 interfaces, and they were we looked at a pretty broad spectrum, I think, in terms of this was the simplest one, a simple button thermostat, probably fairly inexpensive, and all the way up to a computer web interface. So with respect to the simplest model here, we have, we called it the button thermostat because you can see this cover here. This actually comes down and hides this set of buttons here. These are the buttons that are available all the time for the user to look at. And so you can see some of the features perhaps you don't use as much, like programming, are kind of hidden away. And if you want to just change the temperature, well, you can do that up here. It also has the instructions there. This is the next thermostat we use. We call this a hybrid because it had both a touch screen and buttons and switches. And in a sense, this might have seemed like a good idea at the time, but I think it ended up, in retrospect, it seemed like people were very confused by this. If they saw buttons, then they didn't think that you could actually touch the screen, or vice versa. So it's like if you can touch the screen, then why would you have buttons? So it led to, I think, more confusion than perhaps it was worth. It also doesn't, I think it doesn't really look like a touch screen. The size of the screen is just a little bit larger, and it's not like, I don't think the buttons here, like that doesn't obviously jump out at me as something that you could push. Actually, this temperature here, number here, you can actually push that, and it's not obvious that that's an actual button. right? That you would toggle back between the current temperature and the set point temperature using that. This is a full touchscreen thermostat, Honeywell. And it has actual, I call these switches, they're kind of virtual switches here in terms of turning on and off the fan or the heat. And then it has kind of a set of buttons here that leads you to other screens that you can scroll through to get other features. And let's see, next is an Ecobee. We call this our smart thermostat. It was a connected thermostat. So it actually had a web interface, which is what I'm going to discuss next. And this was probably, even though it was a device on the wall, it was similar to a computer in that these were kind of menu-driven. You pressed a button and you got another. It felt like you were looking at a menu, and it had that kind of look and feel to it. Okay, and then this was the web interface for the Ecobee. And you can see right off the bat, it has this display, a tabular display that shows the different temperatures based on the time of day and the days of the week. So this is the home screen. You can see your switches there and the current and set point temperatures there. Okay, so now there's a bunch of these graphs, and I'm going to walk you through these a little bit. Basically, this shows three things. I'm showing the task. And we thought this was the simplest one. This was basically go up to the thermostat and set it to heat. Don't do anything, just set it to heat. You don't have to set it to any temperature. Turn it on, basically. And at the top here shows the % success. So there's about 13 people or so per thermostat. And it shows you 100% of the people with the web thermostat were able to complete this task. And across this side, it has the time, right? So it shows how long it took them to do it. And I'm showing the completed tasks as well as the incomplete tasks. Now, incomplete task basically means either the person says, I gave up, I don't know what to do, I'm done, or they actually did it wrong. They did something and they thought they were done, but they actually didn't complete the task. So it includes both of those. And you can see there's quite a range here. You know, of the hybrid thermostat, half of them couldn't even turn it on to heat. So you can see that usability is kind of an issue, you know, with respect to the simplest, probably one of the cheapest models out there. And some of the reasons, this is what I was trying to get at, where, well, the two with the highest success, the switch, the heat, cool, off switch was visible at the home screen or default level. If you look at the lowest success, the switch was hidden under a cover. And there was actually several people that never figured out that there was a cover there. There was no affordance on it. There was no little arrow or anything that suggested it was a cover. So, oh, I'm sorry. One thing I forgot to mention here is what I'm calling path length. I don't know if you can see this way down at the bottom. But the idea here is that how many steps did it take to do the test? Whether it was I lifted up the cover, I switched it. You know, so that's 2. You can see the path length here wasn't very long, but the fact that the first step was really difficult was a problem. Yes, please. So there's 31 people. Each person tested 2 interfaces. Yeah. Yeah. So, and you can see that, you know, obviously path length was longer here, but you know they still more than half managed to do it. So it was useful to look at all of these things. Okay. So now I'm looking at the second task. Again, all 5 thermostats, the same format, and with this was to set the time in the day. And one of the things we discovered in the survey is how many people actually didn't have the correct time and day on their thermostat. And if you can imagine, if you have a programmable thermostat and the day and time is not right, you're not going to get what you want out of that. And so this is a pretty important task, we thought. The web thermostat obviously was connected, and so we didn't have to do anything with that. For whatever reason, the touchscreen only allowed you to set the time, not the day. But you can see, again, the relationship here between the success rates, quite a broad range. So the touch screen actually had a clock button right at the home default screen. So I think that led to pretty good success here, that it was pretty obvious. And the hybrid actually had 2 means of accomplishing this task. You could either press on the time on the screen or go through a menu and solve it. So I think between the 2, more people got it. I think that was helpful. But with the smart thermostat, you had to press more, then settings, then preferences, and then you get to the clock functions. And it seems like with every decision point, there's an opportunity for someone to get lost. And I think that's what happened here. You look at the path length, and it was quite long. You know, I think that contributed to the failure rate, basically. Again, the button for this was hidden under the cover to set the time. So that led, I think, to lower performance there. Okay, the next task was to identify the current target temperature. So what's the set point right now, right? Not the room temperature, but the set point. And you can see there were basically 3 thermostats that had both temperatures displayed. And so then you got at least a 50-50 chance of guessing which one it is, right? And actually, but these were actually labeled, so that even helped more. But some people, they're not familiar with the term set to. What does that mean? So, but you see pretty high success rates with these 3. Yeah, so it showed both temperatures. And the other 2 didn't have both shown. And so with the button thermostat, you had to press up and down on the arrows to actually see what the set point temperature is. And with the hybrid, you had to press the screen where the current temperature is, and it would toggle to see the set point temperature. Completely non-obvious. So just a few people got that. And you can see how long this one person, what it take them over 3.5 minutes to figure that out.
Do you have an audio recording, and were there things that you had to bleep out?
Yeah, actually, yes. The researcher, Daniel Perry, who recorded all this, he did an incredible analysis where he actually went through every single video and tallied what people did and their comments as well. So he had like a little column. It wasn't the expletive column, but it was something similar. When people expressed frustration, he actually counted that. Pretty neat. Yeah.
These people did the tasks in sequence?
They did.
So at some point, they probably figured out how to open the cover.
Some people did and some people did not.
For all 7 tasks.
Yeah. Yeah. You're right. So there was some kind of learning as you go through, but not in all cases. So this is the 4th task, identify a future target temperature. So this was, what is the set point Thursday at 5 o'clock? Just so you could know what the temperature might be. And you can see the rates dropping quite a bit. As I mentioned, the web had the schedule right on the home screen. And so what you actually had to mouse over it, and then the temperature number would pop up, and you could see what it was. But it was right there on the home screen. So I think that's why we got a pretty good success rate. The smart thermostat had a program button and a tabular schedule, so that was good. I think it's much easier to read when you have time of day and days of the week in a graphic format. The touchscreen it was called a Schedule button. And I've seen on different thermostats, it'll say prog for program. So part of it, too, is the nomenclature, that people may not be familiar with these terms and may not understand what term gets them to where they want to be. And the hybrid thermostat, if you press on menu and then scroll, and then you could select it, and then next. So it was, again, a series of operations to get this. You had to actually go through each mode to find out the day and the time that you wanted. And the button was, one person got it after 1.5 minutes. They probably have one of these at home or something. It was serial access. So you had to go through, again, every single time. At least the hybrid allowed you to skip a day. But this one, you had to go through every single one. It was serial access to it. And again, the cover was over the button. So if you didn't get that the button was under there, you were lost already. Okay, the final task was to look at, set it for away or vacation. And you can imagine with a programmable thermostat, one of the energy saving features would be to turn it off when you're gone, right? To basically turn it down. And you can see the success rates here. There, 3 of them had a specific button that said vacation or away or energy savings, and in addition to a hold mode. There were a few different ways that people could accomplish this task, right? They could go to a specific strategy like vacation mode or away mode. They could just put the thermostat in hold. And some people got so frustrated, I think that's why you see the times of, 5 minutes up here. Yeah, look at that guy. 10 minutes trying to figure this out and was unsuccessful. People would go through and actually program for every single time of day and every day of the week. Well, a couple people did that as their strategy. So you can imagine if you're walking out the door on a vacation, of all the things you've got going on, you're not going to go over to your thermostat and try to figure out how to put it in vacation mode, right? So in the hybrid, you had to actually press the hold on the screen. I don't think it's obviously a button. One person got it after, 5 minutes. Probably random, too. You should see these videos. They're incredible. People are just touching it and doing anything they can to try to get it to respond. Okay, so you don't have to look through all this, but one of the things I developed was looking at my original guidelines and looking at the thermostats across here, tried to say, okay, this was a good example of following this guideline, or gosh, this was a violation. There was a cover here, so you couldn't see the visibility of available options. This was a violation of that guideline. So I went through all of these, and you can see that every thermostat has at least something positive, but you can also see that the ones that were most successful did tend to have more positive features, and the ones that were less successful did tend to have more violations of these guidelines. Things that seemed to be important was this visibility of available options, consistency in standards, and feedback were kind of the three main things. And one of the things I looked at too was, so I looked at these, I just mentioned these, from the existing guidelines, we kind of pulled these out as some of the more important ones. Terminology was also a big thing. But also, it seemed to me that there were some guidelines that were missing. I mean, obviously, I didn't look at every single guideline there is, but I did try to cover the bases. And so one of the things I thought would be a good, if I'm creating a new set of guidelines for programmable thermostats, having a broad and shallow decision tree. And the idea here is that you have the most of your choices at the home screen or very visible, and you don't go too deep. You don't have 10 layers, because at every decision point is a place where people can get lost. And so the idea here is to try to build this decision tree as broad and as shallow as you can, so that people don't get lost, and you can increase your chances that they'll actually accomplish the task. And this is not, I went back and actually found a reference to this under Schneiderman. So in 1988, he came up with this idea or something very similar. Hierarchy of display. Often with these thermostats, you see the display for the set temperature and the current temperature neck and neck, right, the same size, where actually you would probably look at the current temperature more often. So it's nice to have a more of a hierarchy so that the important features really jump out at you, and then the other ones kind of fade away in the background. Affordances, switches should look like switches. Covers should look like covers. There should be some affordance or marking or something on there that shows that you should push this or you should open this. And navigation, this was a big problem. People often didn't know whether they were editing or viewing. As I was talking about with the program, so 3 thermostats had an ability to look at the schedule. Just look at it, just view it. The other 2, you had to go into edit mode to look at it, okay? And then that's rife with potential problems in terms of if you think you're looking at it and you hit something and it gets saved, well then all of a sudden you're heating to 78 or something like that. So big problem. And a lot of people, especially with even just looking at the switching it to heat, didn't know whether, well, am I saying that the heater's on right now? Is this a current state of being for this system? Or am I viewing, or am I seeing a current state, or is this actually setting? Am I actually setting the system? And then recovery from errors would be a big help too in this. So we had very specific recommendations too, and some of these have been mentioned in terms of covers should, I would consider no covers. I have a thermostat at home where someone took off the cover and have left it there, and I wouldn't have noticed that there was a cover there. It didn't make any difference to me. The graphical or tabular form to look at the temperature set points seemed to really work for people, so I think that would be a good thing to include in future designs of programmable thermostats. Use confirmation prompts. Often people would do what they wanted, do what the task required, but then not save. So there was no prompt that said, "Are you sure you want to leave this before saving?" And that would have been a huge help. And use plain English whenever possible. There were things like span and sked and prog and things like that that are just really nonsense words. And again, I think I mentioned this. Use clear affordances. So the next steps, I'm still trying to figure out what to do with this information. The EPA is trying to get manufacturers to come on board and to use our usability metric. And there's, it's I think $60,000 to run these tests. So the manufacturers are really balking at this. And so I'm wondering if it's possible to use some of these guidelines to do a pretty quick and dirty evaluation of a thermostat before it would go through this usability testing. I don't know if that would be something useful or not. And the next step our group is doing is really trying to connect usability with energy consumption. So we're looking at trying to do some field tests with respect to that. So now I'm going to jump into advanced thermostats for campuses. So this is the second research project. And again, I was really looking at 4 different things. I was looking at occupancy sensing, so how do you use occupancy information to save energy, to change the set points to reduce heating or cooling. Advanced algorithms such as learning, whether it's learning in your house or equipment or schedules or temperature preferences. And that I think that's what Nest is really selling, is that, reduced input required by the user. Let's not worry about usability. Let's just not have them interact with the thermostat as much as they need to, or as much as they do now. Engaging user interfaces. So I want to include usability in this, but also I can't tell you how many people have said to me, I don't even want to touch my thermostat. It's just ugly. It's just this plastic box on the wall, and it's not engaging. Well, you look at the Nest, and it's beautiful. It's a nice looking thermostat. It looks like you want to, it's engaging. And you can see even with the top line thermostats now, the touchscreens are getting bigger. There's more color. There's more graphics. And I think that's a positive mode. Network systems. So in multi-residential applications, this allows one manager to access and change a bunch of settings. Very positive. In a single residential dwelling, and you can have it in your house, your smartphone might interface with your system, or you can control it through the web, especially for programming. This might eliminate some problems. And I just looked at a few different thermostats, mostly just to kind of get a sense of what was out there. So in terms of looking at the speed program, we thought, well, dormitory seems to be a natural fit. The occupancy is variable and often very low, for weekends or for vacations and such. And the heating and cooling is often the highest expense. So it seemed like a good place to do some energy savings. Basic equipment was a thermostat and an occupancy sensor. This could be either on board. Some of the simplest ones, cheapest ones, are just has an onboard sensor, or remote. You have something you can stick to the wall or ceiling, or so forth. The way occupants are sensed, either through infrared or through light. This is especially important, as you can imagine, to distinguish nighttime versus unoccupied time. You want the thermostat to know the difference between those two. And one thermostat company deals a lot with door closures. So it senses a door closure, and then it looks for occupancy before or after that period. Wireless versus wired, you still see both, and battery versus power line for the sensors and for the thermostats. In terms of the different control options, obviously when occupancy is not detected, you want to turn down the heating or cooling, right? Not have it cycle as much to be able to save energy. There's some interesting things that are with Telconet is doing some work with these learned recovery times. And the idea here is you're measuring how long it takes for the temperature to recover. So then it decides how low to let the temperature go, right? And this is a constant. It happens continually, right? So you might have a situation where in the wintertime the sun is low, and so this one room is getting blasted with heat. Okay, well that's a situation where and looking at how quickly it will take that room to recover. The idea here was within a 10-minute period is what a lot of what the folks at UC Davis set, that the temperature could come back up to speed. So 10 minutes after an occupant walks into the room, the temperature is reset back to their comfort level. The folks at New York University said that this was pretty key in being accepted by the occupants. Range stops, this basically prevents the thermostat from doing, or prevents the occupant from setting the thermostat however they want. So typically you stop the heating at 70 degrees or the cooling just down to say 74 or 76 or something. And this was, I'll talk about this a little bit later, but in some of the dormitories on the East Coast that I looked at, they were heating to 78 and cooling to 65. And so you can imagine just putting in range stops saved a lot of energy. So, and other things like auto fan reset and pipe sensor. So there's different control options here. And then network, a couple different ways I've seen the network. Of course, they don't need to be networked, and that's another option, but the network does provide value. This is Telconet system where you take the thermostats and you have these gateway servers, and then they kind of gang up to this data center, and then the facilities manager can actually go online and take a look at all the thermostats and whether a room is occupied or not. Another way that they're used is part of a BMS, so it's actually more of a centralized control. It depends on how the HVAC equipment typically is set up. So I looked at 4 different installations. The one in UC Davis was really just getting underway as the study went on, so there wasn't as much information. So I went back and I looked at Harvard Law School, installed a number of years ago, and it was using an INCOM system, non-networked. And then New York University. New York University is doing a lot with respect to sustainability. And so they had, they started off with 1,500, and I think they've got over 4,000 now. I'll talk a little bit later about this, this range in terms of the return on investment, the savings. Basically, the first ones they installed was the very first ones that Telconet installed in any dorms. And there was a huge learning curve. There were a lot of callbacks. There were a lot of problems. I'll talk about that in a minute. But the later ones were a shorter payback period. So to talk about the energy savings, it's really dependent on a number of things. Obviously, the existing runtime makes a big difference. So the colder climates actually are going to have more savings than mild climates. In fact, the manufacturer from INCOM told me that there are places in California he probably wouldn't install this technology. It's just the climate is too mild. Santa Barbara, for example. Building insulation, obviously, if it's poorly insulated, it's going to use more energy. Equipment efficiency, again, the same guy at INCOM said to me, you know, there's some systems I probably wouldn't install. If it's a high efficiency fan coil system, probably wouldn't install the system. You're not going to, the system is already fairly efficient. You're just not going to see the payback periods of less than 5 years. And then previous set points, I mentioned this with the New York University. The project manager was telling me she was seeing students dressed in t-shirts and shorts in the middle of winter where it was freezing outside. So it was kind of a clue that they were really overheating their rooms. And it also depends on the occupancy. Dorm rooms come in different sizes, right? So you see some single occupancy, much more likely to be unoccupied. Once you get to 2 people, 3 people, 4 people, 5 people, well, then you're going to get less instances of unoccupied. So the technology is not going to really do as much. But even with that, typical savings that I'm seeing in these different projects is between 20 to 30%, which is nice. The costs, again, range from $100 for the simplest non-networked system. And this was, again, for the first dormitory that Telconet ever installed, there was just a lot of problems. And they decided to hardwire the installation, so both the thermostats and the sensors. And that just a lot more labor there. So that's what they decided to do. So you can see now the systems are really more in the $250 or $300 range for networked and installed systems. So in terms of the lessons learned, communication was pretty critical. Engaging students was a big part of it. Letting the maintenance people know what was happening. This is a tool they could use, especially if they were networked. These were tools they could use for diagnostics. Location of the occupancy sensor. This is one of the problems with the first Telconet systems is that they installed them on walls. The students came in and moved furniture in front of the sensors. Or I think they installed a couple where they could, the sensors were actually viewing the warm currents from the return, and so that was a problem as well. Not understanding the heating and cooling system. At UC Davis, there was 5 rooms that were served by a single fan coil unit, and there were existing thermostats there, so they replaced them with these Telconet thermostats. But what they didn't know and found out later when they saw no savings, that the BMS system was using the temperature in the hallways to control the system. And so people were cranking their thermostat right, left, and center and not getting anything. So part of it was that they just didn't fully vet the system before they installed it. What's remarkable about this story is that at UC Davis, the facilities managers, even though they saw no savings, continued to install the occupancy sensing thermostats in other dormitories because they loved the networkability. They loved that communication, being able to you know, when vacation starts, they could take all the thermostats and turn them off or turn them down or what have you. So they really valued that so much that they went ahead and continued installing them. And I've talked about this. The guy at Harvard said to me, if we were thinking about this again, if we were to do it again, we would have used some sort of pipe sensor so that the thermostat isn't calling for heating when it's you know, in the middle of summer or something like that. And this was another issue at Harvard, older systems where there was no neutral wire. They basically took a 3-speed fan and turned it into 2 speeds and, you know, used the middle for the neutral. So not a big deal, but something to helpful. Now, so I'm going to just show a bunch of screenshots from Davis. So just so you get a sense, this is from the Telconet interface. And so you can actually dial into a room and see when the gray is when a student is there, and the white is when they're not and when they're gone. So you can see the thermostat is dropping to temperature, a lower temperature when they're gone. This is another room that has a long vacancy. And just to note here, the thermostat is off here and it's on here. So that's the difference between this portion and this portion. You can see once it was turned on, then it came up to temperature. But you can see how the temperature dropped down when the building was, when the room was empty for a weekend. Just a note about occupant behavior. One of the things that New York University really tried to do is engage students and in letting them know how the system worked and all that. And so there were actually, this is from Davis, but it was actually remarkable how many students would actually leave the thermostat off when they were in their room. And some of them would just turn it off when they left. So really great behavior. And actually, Telconet, we talked to them about this in terms of our analysis. We said, we really want to see the difference between, is the thermostat saving the energy or is the student turning it off saving the energy? That's a big deal for us. We want to be able to report on that. And so they changed the interface so that we can now analyze that. We can actually distinguish between when the student turned it off versus when the system was, it was on, but the system was turning the temperature down when it was unoccupied. So this is again, that one room is just looking at, you can see the load factor. This is the room where it's, there's very low periods of unoccupancy. And you can see that the load factor is still pretty high. And then this is you can just see the correlation between when the system is, there's much less runtime on the equipment here. This is comparing the two together. So one of the issues with Davis is that they just installed the sub-meters, I think, within the last month or two. And so we've seen differences. We've seen a reduction of the chilled water use, but we don't have a number on how much it's saving the university yet. So we should have that in the next few months, get an actual number of how much money we're saving, as opposed to just reduction of load or these visuals that show us the system seems to be working. So just to summarize, I think I'm trying to bring the point here that usability, we know that it's not the only factor with respect to the adoption and use of these programmable thermostats, but we certainly think that guidelines and better usability will improve the chances that people will actually engage with and use their thermostats to save energy. The conclusion basically on the second project was that advanced thermostats in dorms seem to be an appropriate use. They save energy during times of vacancy, and the facilities and maintenance people really enjoy it. There's the guy from Harvard was saying to me that what they used to do is they would have someone go into each room during vacation and change the temperature set point. And so having this ability to just change them all at once was really a big help to them. And the guy at New York thought that the advanced recovery increased acceptance by the students. If the student knew that once they walked into the room within 10 minutes that the temperature would be at comfort level, that helped them kind of accept this technology. So I mentioned that we're still analyzing the UC Davis system. So that's it. Thank you very much. And I'm happy to take your questions.
Thanks, Therese. So let's open the floor for questions.
Please.
I understood you are a psychologist, is that right? So how effective is in these thermostats, they are supposed to save energy, to put the cost they really save? Like, for example, you can see how much really are you paying or, in real time. We say $1 an hour or 20 cents an hour, or do you think that's more effective than adjusting temperature, especially for people that have their own homes?
Yeah, thank you. I think that's a great question. And some of my previous thermostat work, that was one of the suggestions I made, that the more feedback you can give people, which if you tell them, raise this temperature by 4 degrees, you're going to save X amount, the better. The more really targeted information you can give people, the better. So I think that's a great suggestion. What's that? I don't know. It does seem that there is more interest in this, and I think it's going to be easier now that you're seeing more kind of smart thermostats and the ability to do that in terms of learning and things like that. I think one problem that I've heard of is that you can't get it wrong. You've got to be pretty close to right, because as soon as the occupant looks at something that you say and doesn't believe it, you've lost them. And so that's what I've heard, and that's been the problem, I think, with smarts all along. I've heard a number of people say, I mean, the adaptive recovery and things like that, Honeywell and others have tried to implement smart algorithms and thermostats for a while. And if they don't work, I mean, that's the story that I hear from a lot of people is that, oh yeah, that smart feature on this thermostat, I just disable it. And this is from contractors who get the callback saying, I disable that feature because so many people complain about it. So I think that's the biggest problem is that if you're going to have a feature that says, you know, by increasing the temperature in the summertime by 4 degrees, you're going to save $20 a month or whatever, that's got to be fairly accurate, or else you just lost your audience. So, good question. Thanks.
Hi, we've talked about the issue of the notion of setback goes back to the days of heating only, and at night people like it cooler. What do people do with air? I mean, I live in Berkeley, so I don't know the answer to this, right? What do people do with air conditioning in the summer? Do they actually make it warmer to go at night, or do they follow the biological thing and make it cooler?
Good question. I think, so you can look at the example of New York where you're not allowing them to set back to 65. So only setting back to even 74 was a savings for them. But I think that's a really good point. It's something that I'm also very interested in. I know there has been a study that looked at what people actually set their thermostats to compared to what EPA recommends, and that was one of the findings is that people tended to set their thermostats low in the winter. They were fine with that, but not in the summer. I mean, I think the EPA was saying 78 degrees, and people weren't setting their thermostats at 78 or even higher, 82 at night. I think so. There's two things going on there at night. I talked to Chung Wei about this when I was writing my dissertation. She was very helpful because I was looking at that issue. And yeah, there is a hard stop for the cooling, for the temperature at night. You can't get above, I can't remember what it is, if it's 80 or 82, depending on the humidity. People just can't sleep, right? The other issue there is once they do fall asleep, they're less aware of the temperature. So there is some room there. And typically, not everywhere, but typically temperatures do drop at night. So, but it's a good question. I don't think it's been well studied. Yeah.
I have a question. I have to go back to one of the slides.
Sure.
It's just to help me understand the slide. Oh, that's a good one.
Okay.
During that vacant period, you can see the temperature I guess it oscillates a little bit during some of those periods. I'm just kind of curious what's going on there.
I'm guessing that there was a hard stop at 66, that for whatever reason, because if you look at, this is the same one, right? It's actually showing the system is going on to cause these spikes. Now, I was curious about that too. It wasn't just,
Well,
yeah.
it's mandated by your tolerance for how long it can take to heat
Yeah.
back up once the
I
occupant
think so,
re-enters, right? If you say it has to come back within 10 minutes to
Right.
the comfort level,
Right.
you can't let it drop below a threshold. So
It's caused by trying to make sure it gets back to that recovery within the 10 minutes or whatever.
Right.
Yeah.
So if you relax the 10-minute constraint, presumably it would allow the room to cool below 66.
Right, and so there's potential for this to be even smarter, I suppose, too, in terms of if the room isn't occupied, and maybe doing some probabilities, right? If the room is not occupied for a day, then maybe you think, okay, maybe the second day, the probability, and slowly ramp it down. But they're still very interested in trying to keep within this 10-minute range, at least initially, and maybe they can stretch that in future iterations.
Okay, I think that's all.
Janie.
Jenny?
Your answer doesn't totally make sense. I'm just lost on one thing. It doesn't
Sure.
completely make sense because on Friday before noon, you see that it does go to like 65. What's going on there?
And if you look, the thermostat is off. Is this what you're talking about? The thermostat is off here.
it's off for a while, but then
Right.
even
Yeah, the
when it's
temperature does
on,
drop
it
down to 65.
stays.
And then it's on, and so now this is the Telconet occupancy sensor saying, oh, the room is not occupied, I'm going to drop the temperature down.
It's not easy
Might-
to see the distinction between the.
No, it's not. Yeah, but so this black line here is showing that the thermostat was actually turned off, and then the rest of it is turned on.
Okay.
Yeah, I should have labeled that better, yeah. Ed?
Wait.
Does this smart thermostat figure the time constant for the 10 minutes recovery? Actually, as from previous examples?
I think that's how it works.
Remember, we had this big difference in the time constant when the thing was going down versus coming on with the air being circulated.
Yeah, I think that's how this works. I'm not exactly sure. It's a patented technology, but I mean, other thermostat manufacturers have used something similar where they try to learn. They look at what the outside temperature is and other conditions, and they try to see, well, about how long does it take in these conditions to return to temperature, and so that's how it decides what temperature to go to. Yeah, I don't know for sure how it's figuring that out, though.
Thanks.
Sure.
Okay, I think that's it. Thanks, Therese.
Okay, thank you.